Hi, I'm Dr. T.H. Culhane for Envisaj Mercy, the Environmental Sustainability and Justice League of Mercy College, New York. And I'm with our new Dean of Psychology, Social and Behavioral Sciences, Carol Dean. Welcome.
Thank you.
Good to have you. Sorry for my hands being paint covered. I don't
That's
think
okay.
it translates.
Oh.
Why my hands are covered in paint is we've just finished a prototype of an Envisaj designed solar hot water system made completely with local parts with the exception of these vacuum tubes, these glass vacuum tubes that we brought in from Seattle. And this has been a revolution in the solar industry since Germany invented these somewhere around 2000. Well, I first started seeing them in Germany 2004, 2005. I was the first person to bring them into Cairo, Egypt in 2007, and then the Chinese started manufacturing them, and then we were able to buy them all from China. These are probably made in China, but they ended up in Seattle. There's a shop that sells these for $10 a tube. So for $100, you've got 10 beautiful little solar vacuum tubes. Now, why this is such a miracle is because normally, you remember solar panels, they were flat-plated glass collectors. And what would happen is the sun would move from east to west across the southern arc of the sky, and then at certain points you'd see reflection, as you look here. That shine that's going in your eyes is energy that's not getting into the tube, it's bouncing back to your eye, so bouncing back out. However, from the perspective of the water that's inside these, there is a blue, this is a kind of aluminum nitride solution film over copper, and the water is inside that. Then there's a vacuum of argon gas, and then there's another glass tube, so they're completely cool to the touch no matter how hot it is inside. And then, because it's a vacuum, the inside heats up really hot, and as the sun travels, because these are curved, it's always 90 degrees, so normal to the surface that it's trying to heat. So from the perspective of the water inside, it's always seeing direct sunlight rather than bounce. And that is why they're so efficient. We've got them spaced so that the sun can get at them as it goes, and there's no heat loss. That's why they're cool here. So what happens is that the water, these are all these parts from Home Depot we bought, and that's the expensive part, because normally these would plug into a tank. We don't have a tank, so we're using 4-inch tube PVC from the hardware store. That's about the largest you can find practically, and that's our water tank. We've painted it black so that it will also stay warm when the sun is shining. And then that water tank is being fed by these. Cold water comes in here and fills these. So these are all filled with water now, and this is filled with water. And what happens is the cold water runs down the back because cold is more dense and falls, and then as it heats up, the less dense hot water begins to rise. And when it gets here, the hot water has to go somewhere because more cold water is trying to replace the hot water that's rising. It's called thermosiphoning. And so the hot water rises up here, and rises up here, and rises up here, and behind it the cold water falls because this is on an angle, so the cold water is falling this way and down. And that creates a current that all day long takes that 19-degree water that we put in at 3 o'clock in the afternoon, and now we're at 40.3 degrees. Your human body is 37 degrees. So this is 3 degrees Celsius warmer than the human body. That's bath water. It's actually hot bath water. And that's with only 3 hours of variable sun. It was cloudy a lot today. So we're going to try tomorrow. It's technically supposed to be able to get up to boiling. And we're going to use all of this to heat our biodigester. The flow is going to be from a hose that goes through here. We're going to test that now. And then it's going to come out up here with one of these valves here. And we have multiple valves we can take it from so we can test. Here it's not here. Now if you put your hand under here, you can see.
Oh, it comes.
Yeah.
Yeah.
So, and that's the stuff coming out of the top area where there was a whole vessel of it. And I think if we open this up, still about 40 degrees.
Yeah.
So that's bath temperature. Not boiling yet, but bath temperature is good. That's what the biodigester is like. And if I can show you over here, I'll show you the biodigester. This is one of our biodigesters. It was out frozen here all winter long, so it's not doing so well. The idea of the biodigester is, this is my own design with students' help. We built this, but I designed this for Woods Lotan in Israel, and it's working well there because it's hot. But the food goes in here. This is like compost. This is just the cafeteria waste that we grind up. So food waste gets put in here. That's just a drain. It then has a pipe going down, which is the throat. So that's the mouth, and there's a throat going to the bottom. Then another pipe comes up and comes out here. And then this is the fertilizer that results. That liquid compost tea is what we're using in the tower gardens, the vertical aeroponics that are in the Mahoney Hall greenhouse. Here is where the gas comes out, and I can show you if I pull this for a second. There isn't a whole lot of gas coming out of this, again, because it was outdoors and it froze and we're still getting it to thaw. These are hex coils that go inside that we'll eventually use to heat it, but we haven't hooked them up yet. But if I build up some back pressure,
Oh,
you see once you can see the flame, it's
yeah,
too,
yeah.
you can't really see it because it's too light out here. It's the cleanest flame on Earth, and that's about all we'll get for now. So what we have instead is we have a system in here that we've been gradually heating up. Let me just open this for a second here. And this is an absolute mess because we have such a little space and so much equipment. But this up. So if I climb up in here and move back here, this is tank indoor. This is a water tank that goes to a water heater that has a propane tank that then heats the coils. So we've gotten this up a little hotter. Same thing though, feeding goes on here. Fertilizer comes out there. This is an experimental gas holder where we can measure how many liters because it's graduated. I know it looks like crazy stuff. And then here is the accumulation. And let me find one more thing to show you how clean this is. So if you, I don't know if you can step up in here for a minute. Step there. So here,
Oh,
you see this very clean flame.
yes, yeah.
And you can see when I put it over the paper, there's no soot. You can't find any evidence of carbon. It's the cleanest burning flame in the world. It has no carbon monoxide, so you can do it indoors in the winter. You would never die of asphyxiation because there's no CO. It's carbon dioxide and water vapor that's being released. It's completely safe. It's the same as a natural gas burning. You can put your hand over it. It's not going to hurt you if you want to sort of see. It's it's
Wow.
just it's more. So but it's the same flame temperature as your natural gas oven. In fact, it is natural gas being produced every day from cafeteria waste here at Mercy College. Of course, its flame temperature is hot enough. But you see here, there's smoke. This is what kills over 2 million women and children around the world from indoor air pollution caused by burning charcoal or firewood. Deforestation is caused by this, massive mudslides and floods. All of that can be completely eliminated because human waste and cafeteria waste, food waste, turns into this within 24 hours. And that's what we're demonstrating here with this absolutely clean burning flame that has absolutely no odor. It's a perpetual flame that will never, ever go out as long as people are feeding it food waste or, in some cases, like we're doing in Brazil, also human waste. And it ends the problem of cholera, typhoid, dysentery. Those go away. Rats, fleas, bubonic plague, all the things that have plagued humanity, this eliminates because all those organic residuals get turned into a liquid fertilizer that's quite safe and a flame that's quite safe.
And there's no solid?
Solids eventually will build up at the bottom of the tank. The one in my home in Germany has been running for over 5 years. It's almost 6 years now since my baby was born. We started it with his baby diaper wastes and with our food waste and some horse manure, and it's still going and we've never had to clean it out. And that's because the food waste digests so well, it carries most of everything with it in the liquid fertilizer. Nitrogen rich. It's the best compost feed, much better than soil, which is why we're doing it for soilless growing. But yeah, eventually we may have to aspirate, put in a pump and that's why we have this shop back here. So we could do that. But as you can see the flame, there it is. And it's when it's not lit, if I just squeezed it out, you'd smell a slight odor, which is good because you'd know that there's a gas leak. However, in the fire marshal up in Alaska, the high school where we did this, and then we talked to the building inspector here, they've all looked at this and gone, you know what, this is so safe because it dissipates instantly. Yeah, it's lighter than air, not like propane, which is heavier than air. Methane is lighter than air. It's got carbon dioxide content. It won't spark. Like if I press on it like this and just hit this, if I keep the flame, it takes a lot of sparks to get, see, like it takes several times. So it has a lower flame velocity and a lower, it has a higher flame tip, lower flame tip speed, and needs a higher energetic flame to get it going because of its carbon dioxide content, which makes it really actually quite safe. And then it extinguishes itself very easily. So it's probably the most benign fuel on the planet. In Sweden, they're using it to run buses and trucks and cars and taxis. In Germany, they use it for district heating, generating electricity for entire cities. Bloomberg has made a call that 100% of New York's organic waste and toilet waste will either be composted or made into biogas. When he was leaving office, he said that, and it looks like The new mayor is going to follow up on that. And there's interest from all sorts of foundations. So we like to think that we at Mercy College are training a generation of young people who will understand that zero waste is achievable within their lifetimes.
Although, let me ask about the size of the system. Is sort of a big physical system, and I don't know how much waste you're putting into it to generate.
Right. We need to put in 1 bucket worth per day
Yeah.
to get ultimately at the right temperature, and that's not what we're trying to get up here. When this is at body temperature, because this is an artificial stomach, it will produce its volume in gas per day.
Okay.
And I have a bag that's not here right now. When it starts getting to that, I can fill that bag a day, and that will enable us to cook on a single burner. We'll cook for 2 hours on a day's production of gas, this volume of gas. If you want to cook for 4 hours, you have to double it, so then we'd have to use both tanks. You can't just feed it more and get more gas.
Right.
There's a system that we're building down in the Amish country that we also have the molds from China to build in Ellenville, New York, and we propose to build at Mercy. It's 10 cubic meters, which is the size of this whole shed. That system would produce enough to run a generator for 12 to 16 hours.
But how much fuel does it need to?
Then it would need 10 buckets.
Right.
So basically it would need 2 of those, or actually 3. It needs 3 of these.
All those big buckets. Okay.
Yeah, which we generate much more than that.
Right. Well, I guess that's what I'm thinking
Yeah.
about. The system itself is so physically big, but what it is able to process.
Right. So if you picture a flatbed truck, for example, or a 40-foot container, that size can process a ton of food waste a day. And that's what many institutions are doing. They're coming in with a flatbed, popping the thing down.
Well, there's a lot of cafeteria waste.
Yeah.
I mean,
Yeah.
like if you don't eat the food, what do they do with it?
And it offsets then tipping fees and haulage fees and all of those associated costs, because and the things pay for themselves in anywhere from 5 to 7 years based on the offset in haulage costs and tipping fees.
Well, and probably the sale of the fertilizer.
And the sale of the fur, yeah.
If you're doing it.
Absolutely. That's
Wow.
the big value. And then the gas is locally used, but it does offset your gas consumption. The school I visited in China was 3,000 students, 700 faculty and staff. All of their cooking needs were met. Some of their electric generation needs were met. And all of their landscaping completely taken care of by both the toilets and the cafeterias. And then I visited a university in China, did the same thing. And Kathmandu, 2 universities, places in India, several. So it's pretty well known in those environments. But they're subtropical or tropical. Very few have tried to do it at the university level, except Berkeley has one, big one.
Yeah.
They're big into that. Several of the UC colleges do. And then you have Midwestern colleges that are doing this, but they're associated with farms. And they've got big insulated tanks. We're working more on the do-it-yourself, home-scale level. What's the smallest you can make it and get effective gas.
So in terms of the composting waste from a cafeteria, like a college cafeteria, you have to be pretty clean compost. That is, you can't have napkins in there. You have to have really primarily.
No, actually, if you shred it all, like we use just a
Your grinder.
incinerator grinder and a bucket, and we go around the cafeteria and we collect it and we grind it. If you have grinders in there, and they're heavy-duty enough grinders, and there's one that they make at Incinerator Corporation, that this one's from. There's one called the Waste Express that even centrifuges out all the water. You put everything in there, and even if plastic cups and things get ground up, it doesn't hurt the bacteria. They, in fact, use it as surface area. So many biodigesters, like in Mexico where I've been done some work, the biodigesters they sell have PET bottles shredded up inside of surface area for the bacteria. So it would just be a matter of if you put too much of that in, when would you have to clean it out before it all gets
Yeah, right.
Yeah, but landfills produce a lot of methane, and everything is thrown in.
Right.
So nothing short from antibiotics really can hurt these. It's then just a matter of the cleaning. So, but paper, interestingly, paper can actually be a feedstock if it's aerobically treated before it goes in. So if it's heated for 24 hours with air, then it gets broken down, and then these guys can eat it. Otherwise, it just sits at the bottom, and it makes a sludge. It's good for the bacteria to live in, and then you have to pump it out once every 2 years or so. But there's really nothing that you can't put in.
Okay, so the value of a system this size would be for an individual's home use?
Yeah.
Because it's too small for a university
Yes,
to use.
this is experimental. We just built one, the students from Envisaj, myself, Shivani was up there last weekend camping out. We built for a family in New Paltz. We're going to be building one for with some friends up in Massachusetts, and then we're going to build in Pennsylvania the week after I get back from National Geographic. And that's, individual families, 4 to 6 people, can produce enough waste to cook for about 2 hours a day on this, and 2 of them together, which we generally recommend. We put 2 of these in the basement. That's about 4 hours of cooking a day.
Okay, so then all the maintenance the family has to do is just take their composted food and bring it down to the...
Not even.
Oh.
Because what we did at Kathy Puffer's house is we put an incinerator food grinder into her sink, ran the plumbing down going into here. They just press a button, scrape their plates, and then they just turn on the gas. So
Okay, so and the gas pipes through to their gas stove?
Will be, yeah. We haven't plumbed that part yet, but yeah. And the only outstanding issue is, are they going to store it in inner tubes? Are they going to store it in a floating garbage drum? Are they going to store it in a PVC bag, in an air mattress? The storage of appreciable quantities of gas, the Chinese do big PVC bags. The Indians do large sizes of this, and we're going to remodify this to make it more attractive. But what basically happens is this thing fills with gas and it floats. You can't do it because there's a vacuum. And then as you use the gas, it sinks down.
I see.
And we're going to put a pole. We did this in Germany. We put a pole in the center so it rises up nice and straight, and then it goes down. And that's the Indian style. So, but there's even work that was going on in Kathmandu, and our colleagues in Israel have got a lot of new systems for storing the gas and compressing it. And the market is about to explode. So in about August, several companies, one in Oregon that we work with, one in Israel that we went to visit when the students went out there, and we saw all of their facilities, and one in India, one in Kenya, they're all coming to market with home biogas systems that you can just purchase and plop in, and you don't have to do all this stuff.
Right, so this looks very complex for a home user.
Yeah, yeah. So,
but your goal here was to develop a system that was relatively cheap to produce.
And give the students the chance to really get their hands in from the get-go. Like, how could you build it when you're dealing with whatever's around?
Right.
And that's the creative thinking part.
Yeah.
So thank you very much.
You're very welcome.
Thanks for joining us at Envisaj, and we hope those of you who weren't able to make it for our solar hot water biogas build can see this and learn from it, and then come on and join us on the next one.